Hello everyone, my name is Jieliu. Today I'm very happy to present my work, Lobster, a load balance aware I/O for distributed DNN training. This work was finished by UC Merced and Argonne National Lab. HPC and AI is becoming the driving force for HPC growth. It is predicted that arrive at 2025, there is around 40% of HPC growth from AI. Currently, many scientific applications are already using AI, either natively or combined with simulations. Towards self-driving laboratories, some large-scale robotic laboratories driven by HPC and AI to reduce human intervention. And some laboratories are trying to use AI technology to accelerate discovery in materials, chemistry, biochemistry, biology, and energy. However, training DNN is particularly difficult, and as DNN has becoming deeper and deeper, and training such large models need to use a lot of computing powers, especially in recent years. As this figure shows, from AlexNet and AlphaGo, we can see there is a steep increase in computing power usage when training DNN models. For example, AlphaGo need to use around 3.4 mouse to train the model. In order to scale the DNN training, multiple nodes equipped with multiple GPUs are used. And this figure shows the basic storage hierarchy for distributed training. And we can see there is a parallel file systems. And we have many computing nodes. And some GPUs are collocated on the same node, share node local cache. And the training samples is not available in the node local cache. It can be retrieved either from the external storage repository or from the cache of a different node. One challenge for DNN training is about the I/O contention and scale. And currently, we always use data parallel training. This picture basically shows how the data parallel training works. We have each GPU will have a model replica, and during the training, we have the data pipeline. And data pipeline is used to load data from the repository to the local node. And then we will do the forward pass, backward pass, and then update the weights. At the end of one iteration, and the gradients will be arranged. And because each GPU need to load data from the repository, so that will cause the I/O contention problem. Recently, a lot of researcher has proposed some approaches to optimize the DNN training on the GPU side. But currently, we can see the I/O has becoming the new bottleneck for DNN training. Because ingesting the training data has a very high overhead, and it is a very complex process. And because it needs to assemble mini batches, which include some stages like read from data repository, and basically maybe we need to load data from a parallel file system, which will be very time consuming. And after the data is loaded, we need to do some transformations like data decoding, data augmentation. And then we also need to do the shuffling and batching to avoid repeated fine-grained sampling. So in order to know the I/O overhead well, so first we need to study it. And here we focus on the PyTorch 1.8 and DNN runtime and the Darley for data loading. Darley is an industry standard state-of-the-art data loading library. And we focus on the data parallel training, use up to 64 A100 GPUs. and we use ResNet 50 for our evaluation, as it is a frequently used DNN training benchmark. We use ImageNet, which contains 1.28 million samples, and each sample has a size around from 10 kilobytes to 100 kilobytes. And we treat each sample as a separate file. And during the training, we measure I/O overhead due to the remote reading from data repository. And we also measure overheads of data pipeline stages through instrumentation. And we have some results based on our profiling. And in this figure, it shows the execution time breakdown of the training pipeline for 3 GPUs. And as we can see, each histogram contains the GPU idle time, GPU computation time, data preprocessing time, data decoding time, and data loading time. We zoom on the data pipeline of 3 out of 64 GPUs for various iterations. And we have some observations based on this figure. You can see I/O operations become unpredictable under concurrency, which will lead to stragglers. As a consequence, stragglers delay the whole iteration due to the gradient synchronization. We also have some other key observations. Every training sample is reused at each epoch, and the reuse distance may vary significantly due to pseudo-random sampling. Figure 4 shows the histogram of reuse distance of the training samples. We measured in terms of number of iterations for the reuse distance. Here, if the reuse distance is small, basically that means the data samples will be reused by a particular computing node in the near future. However, if the reuse distance is long, that means the data sample will be used by this computing node after a long time. So based on the reuse distance, that means we need to design a smart prefetching and caching strategy. And we also have some other observations for the data preprocessing. Here we change the number of threads for data preprocessing, and we measure the whole throughput changes. As we can see in figure 6, as we enlarge the number of threads for data preprocessing, at the beginning, the throughput increases. But when the number of threads arrive at a point, and if we continue to increase the number of threads for data preprocessing, we didn't see any improvement, throughput improvement for data preprocessing. That means we don't need to use too much threads for the data preprocessing. Based on our observations, in this paper, we propose Lobster, load balance aware I/O for distributed DNN training. Lobster contains several components like collaborative caching, which means we can get data from remote cache instead of parallel file system to avoid I/O bottlenecks. And it also contains optimal prefetching, as perfect knowledge about future I/O due to PRNG sampling is known. And it also contains a performance model to predict stragglers. And another thing is about the eviction policy based on the reuse distance. This policy is coordinated with prefetching. And finally, Lobster contains the load balancing strategy to optimize the allocation of the threads to the data pipeline stages. For the implementation, we base on the PyTorch data loader. This slide shows the architecture of Lobster. We can see we have the performance model, which is used to optimize the data loading time. And after the data is loaded, we need to do the data preprocessing and finish the model training. So in Lobster, the first thing we need to do is to decide the number of data preprocessing threads. We throttle thread level parallelism in preprocessing so that it can redirect threads for data loading. And to decide the number of preprocessing threads, Lobster predicts the preprocessing throughput based on a piecewise linear regression. The second step in Lobster is decide the number of data loading threads per iteration for each GPU. We introduce a multi-queue data structure to distinguish I/O between GPUs, and then assign threads to GPUs in proportion to data loading intensity. The third stage is to balance I/O between GPUs in the same node. This is to reduce the straggler problems. We formulate the problem of deciding data loading threads as an optimization problem. Then we use a computation-efficient heuristic algorithm to solve the I/O balance problem. For the evaluation, we use Theta GPU as our experimental platform. Theta GPU is an expansion of Theta, originally to support coronavirus research. Now it's open for general use. Theta GPU contains 24 nodes, and each node is equipped with A100 GPUs. That means we use at most 192 GPUs to train our model. For model selection, we use some famous model like ResNet 50, ResNet 2032, ShuffleNet, AlexNet, SequenceNet, and VJJ11. And we use 3 bit lines. The first one is PyTorch IO. This is a built-in PyTorch data loader using a constant number of threads for data loading and preprocessing. The second one is DARLI. It is a widely used NVIDIA library for DNN training I/O. And the last one is NoPFS. It is a state-of-the-art approach that implements detrimental prefetching that is combined with PyTorch. We use 2 different data sets. The first one is ImageNet 1K. It contains 1.28 million training samples. And in total size is around 135 gigabytes. We also train our model on a very large data set, ImageNet 22K. It contains 14 million training images, and the total data set size is around 1.3 terabytes. This slide shows the results, and here we can see we use 3 methods in our evaluation, and the rightmost histogram is about the Lobster, and here we can see compare with the baselines, Lobster has the highest training speed up, and when comparing with PyTorch IO, and we can see the Lobster has at most 1.8 times speed up. And the in figure C evaluates the scalability of the Lobster. We can see we use at most 64 GPUs in this figure. We can see Lobster has among all the different settings, Lobster has the highest performance, and that means Lobster has a very good scalability. This slide shows how the Lobster can reduce the load imbalance problem. We use the ResNet 15 with ImageNet 1K. And for figure A and figure B, and it shows the result of training on a single node and on 8 nodes respectively. And y-axis is about the number of iterations with load imbalance. And we can see for figure A, only 17.5% of training iterations has load imbalance on a single node. And for figure B, we can see only 22.8% of training iterations has load imbalance. And this is the smallest among all the approaches we evaluated. For figure C, it is evaluate the batching time distribution for different methods when training models on a single node with 8 GPUs. We can see Lobster has the least variance in per batch time among these 4 methods. Finally, as I mentioned, during the training, the GPUs can be in idle state, and so which will cause the low GPU utilization. And in this slide, we evaluate the GPU utilization for these different methods. And for different models, we can see the Lobster has the highest GPU utilization. To conclude, data access and preprocessing is becoming a bottleneck for DNN training, especially at scale. In this paper, we propose a holistic data loading I/O runtime for distributed DNN training. We have some observations. DNN training has high I/O overhead, and it also has poor async overlapping between data pipelines and the trainings. This is due to the strugglers. And the DNN trainings has irregular reuse distance for the training data samples due to the PRNG sampling. And there is an optimal number of threads for parallel augmentation. This is my whole presentation. If you have any questions, I'm happy to discuss with you.